Okay, so here we are. We're doing the very end of section 6.1. It's only a couple pages in the book, but I wanted to stretch it out because I also wanted to add Leibniz notation. Okay, so we want to talk about inverse functions. And like I said, we're going to throw in some discussion of Leibniz notation. Okay, so we're going to start with inverse functions. Let's explain our setting. So we have a differentiable function. F. And let's say it has an inverse. Okay, now we would denote that inverse by f to the minus 1. That maps from the range of f, which is f of a, back to the real numbers. And here is our question: what is the derivative of that inverse? Okay, that's the question we're going to seek to answer today. As an example for why we might want to do this, what if f of x is x to the n? So f inverse is x to the 1 over n. Now, we know the derivative of f of x. Okay, we did this last time. Okay, we did that straight from the definition. We just expanded the fraction and computed that limit. But what we haven't done is we haven't taken the derivative of x to the 1 over n. Okay, I mean, you know the answer from calculus, but we haven't proved it here, right? Any questions so far? Okay. We're going to have two results. The difference between the two results is simply the hypotheses. Okay? The first result is going to have stronger hypotheses than the second result. And therefore, the first result is going to be a lot easier to prove. Okay, so we're going to start out with the easy one. We'll just call the easy one a proposition. So we're going to have an invertible function and we'll call its inverse f to the minus 1, which will map from the range back to the reals. You know, when I say back to the reals, I mean, I could also write a there. It doesn't matter. If f is, we're going to assume it's differentiable at a point in a, but here is the really strong hypothesis. We're also going to assume that its inverse is differentiable at the point f of x naught. Okay, and I'm just going to name that point y naught, so we don't have to keep writing f of x naught all over the place. Then our proposition says what the derivative is. Does anyone remember what the derivative of an inverse function is?
Is it the derivative, something like the derivative of 1 over x, or 1 over f of x, something like that?
You're close.
Close, something.
Anyone else, or anyone who's read ahead? Fine, I'll just give you the answer. It's 1 over the derivative of f. Okay. But notice that these two derivatives are taken sort of different places, right? We're talking about the derivative of the inverse at y naught, and we're talking about the derivative of f at x naught. Okay. Now, in the last lecture, we made a big deal about cluster points. Okay, I just want to note that in order for f to be different, oops, it's not the tool I wanted. In order for f to be differentiable at x naught, that means that x naught has to be a cluster point of A. And in order for f inverse to be differentiable at y naught, that means y naught has to be a cluster point of f of A. Okay, so I'm not going to say that they're cluster points. That goes without saying because it's assumed if they're differentiable. Okay, unless there are any other questions, I will go ahead with the proof here. It's very simple. Let's look at the function f inverse composed with f. Okay, what does that do? That maps A back to A, right? Assuming that f is invertible, if I apply f and then apply the inverse, I get back to what I started with. So this thing is the identity function. And what I mean by the identity function is just that f inverse composed with f at any point x gives you x back. Okay, and now our hypotheses have given us differentiability at x naught and f of x naught. So assuming the differentiability given by the hypotheses, differentiability guaranteed by the hypotheses, well, we can use the chain rule. Okay. On the one hand, the derivative of the identity function, which sends x to x, the derivative of that is just 1. So that has to be the derivative of f inverse composed with f. Okay, but on the other hand, and I should have said that we're using the chain rule here. On the other hand, if you use the chain rule, what do you see? F inverse of f derivative. That is the derivative of f inverse at f of x naught times the derivative of f at x naught. But f of x naught is just y naught, so there you are. And there you go, you got an equation. Just solve it for f inverse prime of y naught, and you'll see that it's 1 over f prime of x naught. Okay, that's the proof. Okay, the big thing that made this proof so easy is that we assumed that the inverse was differentiable. Because we assumed the inverse was differentiable, we got to just apply the chain rule. Okay, are there any questions about that proof before we go on? Okay. So let's look at a consequence of this result. Then we'll talk about Leibniz notation. Then we're going to come back and prove a better result. The formula for the derivative is not going to change. It's just that our hypotheses are going to weaken. In our better result, instead of assuming the inverse is differentiable at that point, we're only going to assume that the inverse is continuous at that point. Okay? And that's the big problem with this proposition. This proposition is not useful for telling us that the inverse is differentiable, because it assumes that the inverse is differentiable. Okay, so that's a big problem with this result. It will not tell us, hey, that inverse is differentiable, for sure. Okay? However, one thing this proposition will tell us is when the inverse can't be differentiable. Okay? And that's that you come over here, if this formula for the derivative of the inverse is of the form 1 over 0, then that's proof that the inverse can't be differentiable. Okay, because no matter what happens, it can't have that derivative. Its derivative can't be 1 over 0. So I'm going to state that as a corollary, but it's really an immediate corollary. There won't be any proof. Can we have a continuous function whose inverse is not continuous? Well, we can have a continuous function that doesn't have an inverse. If we restrict to a little local neighborhood, then yeah, we can always find a little neighborhood. Except for if we're on an interior point of the domain, we can find a neighborhood and we'll be good. Okay. Okay, so here's this corollary I mentioned. If f is differentiable at the point x naught, but its derivative is 0, then its inverse cannot be differentiable there. And let's just go to our x to the n. Let me assume n is at least 2. And then, from what we know from the last lecture, our derivative is nx to the n minus 1. So, and again, I'm assuming that n is at least 2. If we look at the origin, we get a derivative of 0. Okay? So therefore, its inverse cannot be differentiable there. So that's x to the 1 over n. This thing is not differentiable. Well, it's at f of 0 equals 0. And that's true for all n at least 2. Yeah, Benjamin points out that x squared does not have a derivative to begin, does not have an inverse to begin with. Not true. Not true. There you go. I just have to change the domain, right? When we talked about these, we did talk about the inverses of these functions fairly recently at the end of a lecture. At the end of a continuity lecture, we talked about these inverses. And this is what we do on the even powers. We restrict to either the non-negative reals or the non-positive reals, and we can take an inverse.
Dr. Bader?
Yes.
Maybe this is kind of an addition to this, but haven't we been defining the inverse to be the function from the image of the non-inverse to something else? So we're always gonna, we're always just picking a domain that a proper domain, right? Like previously we've defined it as, like if f goes from A to R, then the inverse goes from the image back to A.
Mm-hmm.
So like we've been defining it like that, so our inverse maybe isn't the same as traditionally we've thought of. So that may be...
Yeah, so I think there's a much broader point in your comments, and that's that in calculus you like to think about a function as being, like f of x equals x squared. It's just that rule, right? In advanced calculus, you have to be aware that a function is not just a rule, it's a rule together with a domain. Okay, so when I change the domain of the function, technically I get a different function. Okay, so when we talk about derivatives or inverses, we always have to, a good question is always, well, what's the domain on which this is defined? Does that get at what you were asking, Daniel?
Yeah, I was just commenting on that. Like traditionally we make, like in high school or maybe previous classes, we'd say that it doesn't have an inverse because, it doesn't pass the horizontal line and whatnot. But we've sort of been defining our inverses like this. So we're sort of, our intuition and what we've been taught it previously isn't necessarily exactly what we're talking about now.
Yeah, we're taking a much more subtle approach. So in this class, we would never say that x squared doesn't have an inverse. Not to pick on you, Benjamin, but we would never say it doesn't have an inverse. We would say, it does or doesn't have an inverse on a particular domain. Okay. Okay, so even though you can define, the point with this example was, even though you can define a domain on which x squared is invertible, you're never going to get it to be differentiable there. You're never going to get the inverse to be differentiable there. And again, the inverse is the square root function. And the reason is that the derivative of f at 0 is 0. And we just proved that if the inverse were differentiable there, its derivative would have to be 1 over f prime. Okay. Okay, so that's the end of our first result on differentiability of inverses. This is just a proposition, okay? We're going to end today's lecture with a thing we're going to call the inverse function theorem, which will be much more useful. Okay. Now, what I want to say is just briefly, this is Leibniz notation that we're going to talk about just a little bit. So we always write f prime for the derivative of f. Okay. In calculus, and by that I mean in your previous calculus classes, you often write the Leibniz notation version. Okay, so you write df dx for f prime of x. Okay, or if y is f of x, okay, which is again another thing you frequently do in calculus, but you don't do in advanced calculus, but then you would write dy dx. Okay? And again, we're never going to write these in this class. The problem is, well, there's a few problems that can just lead to confusion, okay? One problem is these dx's. We really don't care what variable name you're using for the input to a function. Right? We don't care what you name the variable that you're putting in there. The point of the derivative is that it's the amount the function is changing, right? And it doesn't matter what letter you use to describe the independent variable. But in Leibniz notation, it does matter what letter you use to describe the independent variable. And that's one reason to not like it. Okay. The other reason to not like it is that it looks like a fraction. And even, you know, if you learn separable equations and if you took differential equations, then in the first week or two you learned separable equations. And you abused this fraction thing. Right? You'd say something, you'd solve the differential equation, dy dx equals yx squared or something. Right? You would abuse this and you would say, oh, well, I'll just solve it, I'll separate it, and I'll get this, right? And then I'll just integrate both sides, okay? First of all, the way they teach separable equations, that's just terrible. Never do this, please. But, I mean, what you should be doing if you have to do it, if you have to solve a separable equation, oops, I want it that way. This is just my editorializing. There you go. That's how you solve a separable equation. You leave the dy dx on one side. You can't split it. It's not a fraction. And then you just integrate both sides with respect to x. And there you go. You haven't committed great sins. Okay. But anyway, the whole point
It
is,
pains me every time they do that in my physics classes. I wince a little.
yeah, it's awful because they're not fractions, right?
You just have
So-
to times the dx, right?
Yeah.
So in the correct way of writing it, can you explain the left side of it there? The integral of 1 over y, dy over dx, and then dx.
Yeah, I mean, so what would we write here? What would we write in this class? We'd write 1 over f of x times f prime of x dx. Okay.
Okay.
And then I hope everything, if you write it like this, isn't everything kind of clear? And you're looking at a chain rule. You're looking at undoing a chain rule, basically.
Right. Okay.
Okay, so that was my excursion into editorializing about solving separable equations. I have to admit, when I first taught d/q, I taught it the wrong way too, until I realized someone explained to me how bad Leibniz notation is. Okay, now, so I've warned you, Leibniz notation has all kinds of problems. It's also where Leibniz was one of the inventors of calculus along with Newton. He was thinking about these quantities like dx and dx as infinitesimals. Okay, so this way of thinking kind of leads you into the problems that Newton and Leibniz got themselves into, and why the version of calculus we teach in this class had to be invented, hundreds of years after. Okay, that said, this notation is really helpful for remembering these formulas. Okay, and I'm just going to show you that. The good side of Leibniz notation. Okay, here's the chain rule. Okay, so let's say y is f of x, and z is g of y. Now our version of the chain rule is that the derivative of g of f at x is the derivative of g at f of x times the derivative of f at x. Whereas the Leibniz version is, on the left we've got dg dx. Oh, I'm sorry, I didn't want to write g, I wanted to write z. dz dx, because z is g of y, and y is f of x, so this is g of f of x, derivative with respect to x. Well, on the left-hand side, the derivative of g of f of x is just dz dy, and then the derivative of f is dy dx. And look, if you abuse this notation and you view these as fractions, those two canceled. Okay. Now, what about inverse functions? Let's say y is f of x. Okay. Well, so then dy dx is f prime in the Leibniz worldview. And so what is f inverse derivative at y? Okay. that is the derivative of x with respect to y. Okay? This just comes out of the definition of how the Leibniz notation works. The derivative of the inverse is how x is changing as the image changes, as y changes. Okay, so it's the change in x over the change in y. Well, our proposition says, the proposition we just proved at the beginning of the lecture, it said in our notation, that the derivative of the inverse was 1 over the derivative of the function. Again, you got to be careful that you're plugging the right things in here. Well, Leibniz says that this derivative, which is dx dy, what am I trying to claim? Leibniz says that the derivative of the inverse is dx over dy. But then his version of the right-hand side of what our proposition says would be 1 over dy dx. Again, you see, well, okay, if we were allowed to treat a dx over dy as a fraction, then 1 over it would be dx over dy. Or maybe I said that backwards. Anyway, this would work out if those were legal fractions. Okay? I guess I'll end my discussion of Leibniz notation by saying it's really dangerous. It leads to a lot of confusion. You should never use it in this class, but used appropriately, it is a nice way to remember the rules. Okay. Any questions on that before we go? And we're going to prove the real inverse function theorem.
I'm kind of confused as to like what the like what's the snag here with respect to Leibniz, like at the end, because I mean, like what's wrong with 1 over dy dx?
Nothing's wrong with it as long as you're careful about it. One problem is we don't like to. First of all, it kind of locks you into using using x as the dependent variable.
Mm-hmm.
Whereas our f prime notation just says, okay, there's one variable in the rule for f. Take the derivative with respect to that, and then I can plug anything I want in there if I, you know. But then the really dangerous thing about it is if you say, well, obviously this is true because I'll treat them as fractions, or obviously this is true because I'll treat them as fractions. That's just not the case. Okay.
Gotcha.
They're not fractions. They're it's a notation that looks like a fraction but should never be treated as a fraction.
Gotcha. So it's just learning. They might look at that and think it's true because okay, they're fraction. That's how fractions work, and they might generalize that to other cases.
Exactly.
Because they're not really fractions.
Yep. And like I showed you with separable equations, if you any time when you want to treat them as fractions, there's another way around it that's better. Is it far superior? Well, in the multivariable sense, in the multivariable case, it's I would say it's even more tempting, Colin. In the multivariable case, it's even more tempting to go with Leibniz notation. I think it's just as wrong. What you really want is, we haven't done this here, but what you really want is like a differential operator. So instead of writing f prime of x, you want to use this capital D as your differential operator. And then in multivariable, you would have a few of them. Okay. That's what you really want. You know, and again, actually, you know, if you want to use this part of Leibniz notation, so like d dx of f to mean the derivative of f with respect to x, then that's fine, as long as you realize it's not a fraction, because essentially you're just using that d over dx as your differential operator d. Okay, but anyway, let's get back to our topic today. I hope I made it clear that for this class you should just use primes. And here is our big theorem. Inverse function theorem. Let's see what the difference between the hypotheses here and the hypotheses of our first result are. Let's let f be invertible with inverse f inverse. If f is differentiable at x naught.
Dr. Goddard,
Yeah.
is this inverse supposed to be from the image FA to R?
Yes, of course. Thank you.
Okay, thank you.
If f is differentiable at x naught, which implicitly means that x naught is a cluster point of A, and I think I'm going to have to add. We'll see where this, if we really needed to add this. I think we're going to have to add that f of x naught is a cluster point of the image. Okay. And now here's the big change. We used to say, in the first result, we said that f inverse is differentiable there. Now we're just going to say it's continuous there. And now one more thing. We're going to assume that the derivative of f is not 0 at x naught. Okay, remember our very first result in differentiability said if you're differentiable, then you're continuous. So we really have weakened our hypotheses here. We've changed from differentiable down to continuous. Okay, you got all that, then your conclusion is that the inverse is differentiable there. And obviously the formula has to be the same as the one we did earlier. Any questions?
So in this proof, we're only going to have to show that f inverse is differentiable at the point, right?
Mm-hmm.
Because we've already done the proposition.
Oh, yeah, I just had that thought myself. But no. The way we're going to show that it's differentiable is by showing that the limit exists. we're going to go back to the definition of the derivative. We're going to show the limit exists, and so essentially we might as well show what it equals at the same time because we get it for free.
Okay.
Okay, so we're not, for the purpose of this proof, we're not going to use that proposition. We could have just gone straight to this. In fact, I think that's what the book does. But I didn't. I have to be honest. I didn't look too carefully at the book's treatment of this. Okay. So we're going to go back to the definition of differentiability. We just want to show that limit exists. Let's write down what it is. Okay. What would be the definition version of the derivative of f inverse? Okay, it would be the limit as y goes to y naught of f inverse of y minus f inverse of y naught over y minus y naught. And we'd like to show that this exists and equals 1 over f prime of x naught. Okay. Let me scroll up. We'll come back to those hypotheses when we need them. Okay. Now we're going to go to the sequential form of limit. Sorry, Daniel, were you saying something?
Did we define what y naught was in this hypothesis?
Yeah, in the sneaky way.
Oh, okay. I must have missed it. Okay.
Okay. Now we're going to do the sequential version of a limit. Okay. So, this is the sequential criterion. Criterion. Yeah, I think criterion. It suffices to prove that for every sequence, now this has to be a sequence in f of a with y not removed. For every sequence in there that converges to y naught, we have this. Okay. So instead of having a limit as y goes to y naught, we've taken an arbitrary sequence that goes to y naught and put that sequence in, and now we want the sequential convergence. Okay. Now, f is invertible. We assumed f is invertible on this entire domain. So we can invert it. We can invert all these y(n)s. What I mean by that is we can define xn to be f inverse of yn well, I'm sorry. We can do that just because f inverse exists, right? Here's the one that takes a little bit of explanation. we have that xn now is a sequence in a minus x naught. Why is that true?
F inverse is only x naught at y naught, and we took out y naught from the y ends.
Yes. Or I might phrase it sort of the opposite way from that, that because f is invertible, it's a bijection. And therefore f maps, since we know that f maps x naught to y naught, it can't be mapping anything else to y naught. So f inverse wouldn't map anything else back to x naught. Okay. And what else do we know? We've assumed that f inverse is continuous. Is continuous at y naught. So we know that, and now we just have to think about what does this continuity mean. F inverse is continuous, so we've got this sequence xn. We know that the limit then goes to infinity of f inverse of yn, which is the limit of the xn's. Well, that has to be, by the continuity of f inverse, that has to be f inverse of y naught, which is just x naught. Okay, and now the one thing we haven't used in our hypotheses yet is that f is differentiable at x naught. Let's use that and see what we get. Okay, what does that mean? Well, that means that the limit, I'm going to use the sequential form now, the limit of the f of xn minus the f of x naught over xn minus x naught, as n, the limit as n goes to infinity of that. Well, we just said the line above that the xn's are converging to x naught. So by the sequential form of the derivative, this is just the derivative at x naught. Now, everything in here is non-zero. On the right, that's non-zero by hypothesis. Okay? The denominator is not zero. Why?
Because x naught isn't in the set we're considering.
Mm-hmm. So none of the xn's are equal to x naught, so that's not zero, right? Okay. One of the limit rules was you've got a limit of a fraction if the denominator is never zero. The limit of the reciprocal is the reciprocal of the limit. Okay? So sorry, I realize I'm a minute over, but we're going to finish this in about 2 more minutes, I hope. Okay, so by our limit laws, the limit of the reciprocal over here is the reciprocal of the limit. Now on the right hand side we've got what we want. We want that to be the answer for the derivative. Well, let me just zoom out a little bit. Let me circle what we wanted. Oops. Yeah. That's what we wanted. Here's what we got. Compare terms, we're done. What's xn? Xn is f inverse of yn. That's by definition. What's x naught? That's f inverse of y naught. That's actually how we defined x naught and y naught in the hypotheses. But about yn and f of xn, well, that follows again from how we define the xn's. Xn is f inverse of yn, and therefore f of xn is yn. Okay. And again, we have that. I'm going to repeat a color here. Can I use black? Yeah, okay. F of x naught is y naught. Okay, so not only did we show the limit existed, we showed that it equals what we wanted it to equal. Okay. This is a bit of a, it's a bit technical, that proof, because you got to keep the f's and the f inverses straight. Okay. But there it is. Yeah, so the big challenge is keeping the f and the f inverse straight. The only kind of place where you have to make a decision about how to prove it is to know to go to the sequential form. Okay, but that's generally a good technique no matter what you're proving. Okay, let me stop the lecture there and